Oh, good morning, everyone, and thank you for watching this presentation. I will also wish to thank my co-authors, Drs. Di Martino, Cocuzza, Avellino, Paternò, and Professors Caliò, Gianfrido, Valenti, and in Polonia. As the title mentioned, the objective of this study is providing insights on the seismic vulnerability of lightweight freestanding objects. To achieve this, an interdisciplinary methodology is proposed involving survey techniques, technology skills, and structural dynamics in order to perform experimental tests on the specimens geometrically faithful to the original study. So the results of this experimental campaign were presented, and also an interpretation in light of a new numerical model that we proposed. Although the great advances that were made in the last decades in the field of seismic vulnerability of existing buildings, only more recently the interest has been growing towards the content. The assets that need to be preserved as a content of buildings usually fall into three main categories, that is hospital equipments, electrical and mechanical machinery, and artworks. The first two categories usually are characterized by simple geometry and good materials, whereas the third category, which is the one that is mainly studied in this work, is usually characterized by extreme features, that is very complex geometry, asymmetry, impairments, and perishable materials. So these kind of objects are usually more vulnerable to seismic events, even moderate. In addition, the codes and the rules only recently introduced the so-called flow spectra to study them. So the methodology that I'm going to present is applied to the Venere Landolina statue, which is the masterpiece of Paolo Orsi Museum in Syracuse. It is a marble statue, which is a copy of a former Greek sculpture. It was chosen not only in view of its artistic and historic relevance, but also for its geometric features. In fact, it's a slender statue with a marked asymmetry due to the weight of the statue burdening on the left leg, and also to the shaping of the drapery. So these are the three main phases of this methodology that we identified as knowledge phase, aiming at obtaining a 3D faithful digital model, the prototyping phase, aiming at obtaining a physical scaled model of the statue, and finally the seismic assessment with the proper experimental campaign and its interpretation. And here there are the main phases that the study goes from the real one to the various digital models until the prototype that is finally tested on the shaking table. So regarding the knowledge phase, there are some activities that were made on site, in particular two surveys made with the terrestrial laser scanner and with a manned aerial system technology that is a drone. So these two techniques and the dense point clouds that were derived were then combined and fit together in order to obtain an accurate 3D digital model that was then further modified in order to obtain a polygonal mesh, which is easier to handle and to export to the main and most popular CAD file formats. So, since the original statue is homogeneous, we know from the spatial dynamics that its response is independent from the mass of the system. So, according also to the lab equipment available at the University of Catania and to the size of the shaking table, we decided to create a physical prototype with scale 1 to 2 with respect to the original, and the prototype was created adopting a computer numerical control milling machine that is employing wooden panels. And in particular, the wooden 91 wooden discs were created considering 91 sections of the digital model. After cutting the discs, they were superimposed also thanks to guiding bars that were conveniently designed. So here there are the main phases of the procedure. That is the milling phase, cutting the discs, and then the finishing with sanding the borders, and then the superimposing. From the original marble statue, which is 1 meter and 74 centimeters tall and with a weight of 467 kilograms, a specimen with height 87 centimeters and weight equal to 12 kilograms was obtained, also considering that not only geometry changed, but also the material. These are the last phases of the superimposing of the discs, and the gluing phases. And finally, we are going to see the final result, which is this one. Well, this statue or this specimen was then tested on the single degree of freedom shaking table available in our lab, which is devised with a displacement control input. Each test was video recorded and post-processed by means of a point tracking technique. It was employed a software able to track the horizontal displacement in a certain point of the prototype. To this purpose, the statue was endowed with several markers conveniently aligned on a vertical line, and from their displacement, the rotation of the statue could be inferred according to this formula. In order to avoid any local loss of precision, the data were also conveniently elaborated by means of a smoothing technique. So then this is the design phase of the experimental campaign with spectrum-compatible accelerometers that were generated, considering as target spectrum the flow spectrum to be considered for the site, and considering that the statue is located at the second and last floor of the museum. In order to account for the size factor, the Froude analysis was applied, which enforces the equivalence between original statue and specimen and scales the specimen of the ratio between inertial and stabilizing forces. In order to enforce the Froude analogy, a scaling of the time axis has to be made by a factor equal to the square root of the scale factor. And then the scaled accelerogram have to be integrated twice in order to obtain the displacement history to be applied to the shaking table. So this is a typical response of the statue and the horizontal response of one of the markers. Then these results are elaborated, and it is clearly recognizable that there is a strong side on around the left edge of the statue and a weak side on the right edge, corresponding to the side where the rotations are higher. So the final part of this presentation is devoted to the interpretation of this experimental outcome. In particular, we noticed that the simple working model proposed by Hausner in 1963 did not give any comparable results with the experimental one. We believe that it is due to the impairments in the contact between the statue and the base, and also for the not perfectly shaped edges. This is a well-known phenomenon that was studied in the past by several authors. For example, Shawa with his 3 linear moment rotation row, the roller rock model by Jouffret, and more recently in 2019 by Bachmann. All these models are based on physical observation. In a recent PhD thesis by Giuseppe Cocuzza, we tried to introduce a model based on empirical assumptions. In particular, this model is able to consider asymmetric objects. In fact, the 2 differential equations are differentiated for the right and left side of the working motion. And the classical differential equations is reached by means of this transition function, which is able to consider imperfections. To this purpose, it can be seen that this kind of blocks usually starts to uplift for a lower value of the acceleration than the theoretical one. And as the blocks leaves the full contact condition entering the transition phase, the stabilizing moment increases up to the limit value where the fully theoretical contribution of the ideal block is restored. And the rotation reach the uplift thresholds. So the moment rotation law assumes this kind of trend. The transition function is considered linear. So basically, the parameters that govern this model are the uplift acceleration, which are lower than the theoretical one, the coefficient of restitution that can be estimated considering by free rocking test by means of energetic consideration, and is considered variable with the impact velocity of the block, and the uplift threshold rotation, which cannot be easily experimentally evaluated and are therefore considered in the numerical simulations as free parameters. Well, basically, these are the results of the comparison between experimental and numerical tests. In particular, it can be seen that the red band for this accelerogram shows that even when the ground acceleration is lower than the theoretical uplift acceleration, the statue rocks. So it is necessary to consider a lower uplift acceleration. Regarding the threshold uplift acceleration, on the strong side, it considered by means of a rough estimation, but it was seen that by preliminary analysis that the response is not so sensitive to this parameter. So basically, we consider variable just the uplift angle on the weak side. So from the comparison, it can be seen that this approach is able to satisfactorily foresee the experimental response. And for a better understanding of the influence of this uncertain parameter, in the bottom right figure, we reported for all the numerical simulations the maximum achieved rotation in comparison with the experimental one. The experimental one for each of the 7 accelerograms considered are the black points. The frequency distribution of the maximum achieved rotation is in most part of the cases centered on the uplift, on the experimental value. So it is in many cases able to foresee the correct maximum achieved rotation. But there are some cases like acceleration 1, 2, and 3, where this estimation is not that precise, showing the unremovable chaotic character of the rigid block motion. Well, the final remarks regarding the novel interdisciplinary methodologies that I just presented, considering the advanced survey techniques, technology skills, and structural dynamics that led to conduct an experimental campaign on scaled, physically and geometrically faithful specimens, also in presence of very complex geometry without the original pieces undergoing any touch or movement. We also try to interpret the experimental results in light of a novel numerical model that showed promising results. And we also believe that this strategy can be applied to design seismic protection devices for the museum content. Thank you everyone for listening, and sorry for being slightly late.